Hi, I'm Patty Betzing. I teach at Eastmont High School, and today I'll be showing you about the addition formulas, and we'll also look at the related cofunction identities for trig. So the objectives for today I have written up here, and basically we're going to be able to use and know the addition formulas for sine, cosine, and tangent, and we'll be using these to evaluate some trig values. And we'll also learn about the cofunction identity, and we'll be solving some problems. So first of all, I'm just going to give you the addition formulas for sine and cosine. A lot of books will refer to these as sum and difference identities. I know our book does. The proof of this last one is in one of the textbooks. I'm sure that most textbooks will have a proof of at least one if you wanted to look at those. I think it's worth looking at, knowing where they came from and kind of how they're derived. So, using those trig identities that we just wrote down, or the addition formulas as they're referred to, we're going to try to simplify some of these expressions. So when I look at this first one, and I look at my list of formulas that I have, I'm trying to find one that matches. So I notice that this one looks a lot like the sine of u plus v. So I'm going to use this and substitute my information of theta and 2 theta in for u and v. So my u is going to equal theta, and my v is going to equal 2 theta. And then I'm just going to substitute it directly into the formula that I have. So I have the sine of, I'm substituting into u plus v, so it will be the sine of theta plus 2 theta, and we notice that we can combine some like terms here, and I can simplify that down to the sine of 3 theta, and that one is done. Now this next one's a little more complicated, just in the fact that instead of just having an angle here, we actually have a sum. So we have a plus b as our first angle, and then b as our second angle. But we're going to treat this exactly the same as we did our last one, and we're going to look at our formulas that we have and decide which one we want to use. So when I look through these, I notice that I've got a cosine times a cosine plus a sine times a sine, which looks like the cosine of u minus v. So this is the formula I'm going to be using for this one. So in this problem, u is equal to the quantity a plus b, and v is equal to b. So I'm going to substitute that into cosine of u minus v, and I get the cosine of a plus b minus b, and I'm going to simplify. So I have a positive b and a negative b, so I end up with just the cosine of a, and that one would be considered simplified. So on the first few that you practice, they're very simple little problems where you're just going to be referring back to your identities or your formulas and deciding which one seems to fit. So I'm going to put a couple problems up here for you to try, and you can either turn off the camera and try them, or you can just wait and we'll go through them together. But we've got two problems. The first one is cosine 2 theta cosine theta plus sine of 2 theta sine theta. Be sure and compare your answers with somebody around you to make sure you're doing them correctly. And the second problem I put up there is a little bit different, but I still want you to just use your formulas and see what you come up with. Okay, so if you had tried these, we're going to look at this one, and I notice that this looks like the cosine of u minus v. So that's the identity I'm going to be using, or the formula. So this will be the cosine of u was 2 theta minus v, which is theta. And then when I simplify that down, you should have come up with the cosine of theta. Now on this second one, this is different than the first two that the first few that we've done, in that it's in a more condensed form already. But on this one, you would need to expand it out and then try to simplify. So on this one I have the sine of, in this case u is going to be theta, and v is going to be pi, sorry. And I put it into my formula. So I have the sine of theta cosine of pi minus the sine of pi and the cosine of theta. Now when I look at this, I notice that I can actually simplify some of these values. So the cosine of pi, if you have trouble remembering those, think of the angle. Remember that pi is 180 degrees. The coordinates at this point would be -1, 0. -1 will represent the cosine value. The 0 represents the sine value. So when I start simplifying this, I have the sine of theta. The cosine of pi will be -1. And then the sine of pi is going to be 0 times the cosine of theta. So if I multiply sine of theta times -1, I get negative sine theta minus anything times 0 is 0, which just gives me the negative sine of theta, and we're finished. So on that one, we simplified by expanding it out, whereas on the previous ones, we simplified by condensing it down. And you have to realize that the problems are going to be mixed around, and you're going to have to do different things on different problems. So you just look at your identities and decide what you can do, and you try it. Okay. So I've got one more for you to try. This is similar to the last one. Okay, so on this one, we see that we have a difference. So I'm looking at the cosine of u minus v, where u is equal to theta and v is equal to 3 pi over 2. I'm going to substitute those into the formula that I have. So I have the cosine of theta times the cosine of 3 pi over 2 plus the sine of theta times the sine of 3 pi over 2. So again, if you don't know those values, you can think about the unit circle, and we know that the coordinates for this point are 0, -1. So the cosine value is going to be 0, and the sine value will be -1. So I have cosine theta, and the cosine of 3 pi over 2 is going to be 0. And the sine of theta times the sine of 3 pi over 2, which is -1. And then I'm going to clean that up. Anything times 0 is 0. And then negative sine of, oops, I forgot my theta. Okay. Negative sine of theta, which simplifies down to negative sine theta. And this was very similar to the last one that we did. Now here's one where the instructions are a little bit different, but the process is very similar. So instead of evaluating or simplifying, they want us to prove the identity. So they're actually giving us an equation that is true, and our job is to just verify that it is always true in the general case. So I look at what I've got here. I've got the cosine of pi over 2 minus theta. I recognize this as being one of my difference identities, so I'm going to just expand this out. I have u equaling pi over 2, v is equal to theta, so I'm just going to put this into my formula and expand it out. So I have cosine pi over 2 times cosine of theta plus sine of pi over 2 sine of theta. Cosine of pi over 2, we should know this to be 0, times the cosine of theta plus the sine of pi over 2, which we know is 1, times the sine of theta. This reduces away, and I'm left with sine of theta. Now, since I'm doing a proof, I should have this equals the sine of theta equals the sine of theta equals the sine of theta. I should have done that as I went along. Okay, so that one would be finished. Now, this actually is a special type of identity. It's called the cofunction identity, and we're going to look at these here next. But this is a cofunction identity. They're often referred to as a reduction formula because it takes the cosine of this shifted angle and just writes it as the sine of one angle, so it's a little bit simpler. So these are the cofunction identities, and we're really just going to be working with these first two. But I wanted to mention the tangent just because the property holds. So when we look at these, I wanted to kind of show you visually what we've got here. So if we have a right triangle, and remember that trig ratios always come from a right triangle. So if this is a right angle, 90 degrees, and let's say that this side here, this angle down here is theta. It's kind of hard to read on gray, I'm sorry. And then let's just label our sides A, B, and C. Now since this is a right triangle, this angle is 90. I don't know this angle, I'm just referring to it as 30, or as theta. This angle up here will have to be 90 minus theta, 90 degrees minus theta, or in radian mode I can think of it as pi over 2 minus theta, since these formulas are written with in radians rather than degrees. So I've got my two angles, a right angle which is 90, and I've labeled my sides A, B, and C. So let's just look at this first one. The cosine of pi over 2 minus theta. So if I want to know the cosine of this angle up here, it's the adjacent, which is A, over the hypotenuse, which is C. Now if I look at the sine of theta, the angle down here, the sine is the opposite over the hypotenuse. So the opposite of this angle is A, and the hypotenuse is C. So we can see that those give me the same ratio, so those would be equivalent. If I'm looking at the sine of this angle up here, so the sine of this angle would be B over C, opposite over hypotenuse. And if I look at the cosine of this angle, which is the adjacent over the hypotenuse, I get that same ratio. So those are the cofunction identities, and they call them cofunction sine and cosine. With tangent, this isn't one that we're going to be using much, but I just want to show you that it holds. So the tangent of this angle is going to be the opposite over the adjacent. So this would be B over A. And if I look at the cotangent of theta, which would be the adjacent over the opposite, I also get B over A. And notice again that I have tangent and cotangent. And the other one that we could look at, it would be the secant of pi over 2 minus theta would be equal to the cosecant of theta. And we don't use that one, but the property does still hold. So let's use the stuff that we've learned so far and look at some problems. Okay. So the first thing we're going to look at is determining some exact values. So we know that we can find exact values for 30 degrees, 45 degrees, 60 degrees, and then all their related angles in the other quadrants. So if I want to find the exact values for the sine of 15, I'm going to use my addition formulas and try to come up with 15. So I want to think of this as sine of, and I want a quantity in here that will give me 15. So I look at the angles I know, and I want to come up with a way to get 15. So the first thing I see is 45 minus 30. So I'm going to write that one down. So 45 minus 30 will give me 15. Now, I also could have used 60 minus 45 to get 15, and my final answer would be exactly the same. So just because you do it one way and the person beside you is possibly doing it differently, it doesn't mean one of you is more correct than the other. They're just different ways to do it. So this is a sum, and I'm using a difference. So my U value is 45, my V value is 30. So I'm going to have the sine of 45, the cosine of 30, minus the sine of 30 and the cosine of 45. I think I flipped those around, but it's still the same thing. So the sine of 45 I know is radical 2 over 2 times the cosine of 30, which is radical 3 over 2, minus the sine of 30 is 1/2, and the cosine of 45 is also radical 2 over 2, just like the sine of 45. Now I want to clean this up, so I'm going to multiply these together, and I have radical 6 over 2 minus radical 2 over 2. And this is an okay way to write your answer. I personally prefer to see radical 6 minus radical 2 all over 2, but they're both correct. So here's another one, the cosine of 105. So again, using 30, 45, and 60, we want to try to come up with 105. Now, if for some reason this number gets too big and you can't get it by adding 30, 45, and 60, remember you do have options like 120, 150, 135. You can totally use those. These tend to be small enough that we can get them with the quadrant 1 angles. So I'm going to use the cosine of 45 degrees plus 60 degrees. Okay. I also could have used 135 minus 30 if I wanted to try something different. So I'm going to use this one. So my u value is 45, my v value is 60. I'm going to substitute that into the formula I have, and I have cosine 45 cosine 60 minus sine 45 sine of 60. So the cosine of 45, I'm just going to plug in the values for these. I get radical 2 over 2. The cosine of 60 is 1/2, sorry, I think there for a second. Sine of 45 is radical 2 over 2, and the sine of 60 is radical 3 over 2. So we're going to clean that up, and I get radical 2 over 2 minus radical 6 over 2. And when I can either leave my answer like that, or I can write it as radical 2 minus radical 6 all over 2. You're going to find that a lot of these answers look very similar when you do them, because we're using the special right triangles that we know, and they're the same three values: 1/2, radical 3 over 2, radical 2 over 2, and then if we're working with tangents like we'll do later, we have radical 3's and 1 over radical 3. Okay, so a new little thing to look at are problems that look like this. So this one tells me if the sine of angle S is equal to 3 over 5, and S is in quadrant 1, and the sine of angle T is equal to negative radical 3 over 4, and that's in quadrant 3, they want me to compute the value of sine S minus T. So for me, I like to think of this visually at first. I'll show you how to do it algebraically also. But I tend to think of it in the coordinate plane. So if this is in quadrant 1, I tend to draw a reference triangle in quadrant 1. So I know that the sine is the opposite over the hypotenuse. And then for this angle, it's in quadrant 3, so I'm going to be down here. And they're telling me that the sine value is negative radical 3 over 4. So again, I draw a reference triangle. This is my angle T, and I have radical 3 as the opposite over the hypotenuse of 4. And I go ahead and leave this negative because it's actually a negative value for sine. When you're working in the coordinate plane, it's really easy to keep the negative values negative just visually. So this is in quadrant 3, so I know that this is negative. Same thing here. This would be a negative value when I get it, although in a triangle the distance is positive. So it's just kind of another way to think about it. It helps me keep my signs correct when I'm doing cosine and tangent. So they want me to find the sine of S minus T. So let's go ahead and expand that out using our addition formula. So I'm going to have the sine of s cosine of t minus the cosine of s, the sine of t. Now when I look at this, I know the sine of s is 3/5, and I know the sine of t is negative radical 3 over 4. I am going to need to know the cosine values of each of those angles though, cosine of s and the cosine of t. Using my reference triangles, if I find this missing side, I will be able to get the cosine. So I'm going to use the Pythagorean theorem. So I'm going to say that 5 squared minus 3 squared is equal to, I'll just call this b squared. So I have 25 minus 9. We probably should know this one just off the top of our heads. But we end up with that side equaling 4. So if this side is 4, I know that the cosine of s is going to be positive 4/5. And I know it's positive because it's in quadrant 1. Now when I do the cosine of this one, I'm going to do the Pythagorean theorem as well. So I have 4 squared minus negative radical 3 squared equals b squared. So 16 minus 3, and I end up with b equaling the square root of 13. Now the distance is the square root of 13, but if I think of it in the coordinates, I'm going to put a negative on there. So the cosine of t is going to be the adjacent, which is negative radical 13, over the hypotenuse, which is 4. So now that I know the cosine values and the sine values, I'm going to plug everything into my equation. So the sine of s was positive 3/5. And the cosine of t is negative radical 13 over 4 minus, and then the cosine of s is 4/5 positive, and the sine of t is negative radical 3 over 4. We'll clean this up by multiplying. So I have negative 3 radical 13 over 20 minus negative 4 radical 3 over 20. I have a double negative here, so when I simplify that, I would have negative 3 radical 13 plus 4 radical 3 all over 20. Okay. Now, there is a way to find this algebraically rather than doing it visually, so I'm just going to show you that really quick, and if you choose to do it that way instead, it's up to you. So if I know that the sine of an angle is equal to 3/5, I can use my Pythagorean identities to find the cosine value. So I know that cosine squared of s will equal 1 minus sine squared of s. So cosine squared is equal to 1 minus, and I know the sine value is 3/5 squared. So I'm just going to go through and solve this, and I get 1 minus 9/25, which would give me the cosine squared is equal to 16/25. And then when I square root both sides, I get the cosine of s is equal to 4/5. Now this is positive or negative, and we have to ask ourselves, do I want the positive value or do I want the negative value? And since I'm working in quadrant 1, and I know that cosine is positive in quadrant 1, I know I want the positive value. So the cosine of s would equal 4/5. So if you prefer to do it algebraically, you can get the cosine value that way. If you prefer to draw reference triangles, you can get the cosine value that way. And they're both correct, so whichever way you prefer is fine. Okay, so as promised, we have addition formulas for tangent. And I saved these till the end because if you look at them, we can think of the tangent of u plus v as being the sine over the cosine. Which now if I just substitute in those formulas, these are very easy to remember because I'm just taking the addition formulas for sine and cosine that are fairly easy to memorize and plugging them in. This can be simplified down to this formula for tangent, which is the one I actually use most frequently because it's a little bit simpler. But you do get the same answer either way. The algebra is not that much different or more difficult with either way. It's just whichever you prefer. A lot of students, I think, tend to prefer this way because it's less for them to remember and they're not working with as much different stuff. Some people prefer these just because they feel like it's simpler, it's faster. We'll try to use both over the next couple days. Okay, so we have those formulas. So how we'll be using those is to simplify some problems. So look at this one. We want to simplify this equation or this expression. So when I look at this, notice it's written in that second form. Be very careful with the pluses and minuses. That's what causes the most problems. So since this is the tangent of t plus the tangent of 2t over 1 minus, I'm dealing with the tangent of u plus v. Okay, so I'm going to use tangent of u plus v. So the u value in this case is going to be t, and my v value is going to be 2t. So this is going to reduce down to the tangent of u plus v, which is going to be t plus 2t, which just simplifies down to the tangent of 3t, and you're done. So some of them will be simple like this, some of them get a little more complicated, but we'll look at a few before you have to do these all on your own tonight. So here's another one where I actually have some values in there. I should have made this one minus, but I actually used plus again. But we notice that u is equal to pi over 9, so we're definitely working in radian mode. V is equal to 2 pi over 9. And the tangent of u plus v will be pi over 9 plus 2 pi over 9. Now this was nice, they have common denominators, so it's going to be very easy to add. And I get the tangent of 3 pi over 9. Remember, I want to simplify as much as I can in every problem. So when I see 3 pi over 9, I need to reduce that down to pi over 3. And then when I reduce it down to pi over 3, I notice that that's one of the exact values, exact trig values that I should be able to evaluate. So I think of my unit circle. Pi over 3 is 60 degrees, so I draw a reference angle. 1, 2, radical 3. So if I'm trying to find the tangent, I want the opposite over the adjacent. So the tangent of pi over 3, or 60 degrees, is just radical 3. So all of this reduces down to radical 3, and we can see that this is a much simpler answer than that. Okay. Now I put another one up here. This will be our last example. On this one, it's not separated out for you, and we just have to find the exact value. Now we did some of these with sine and cosine, but we're going to look at this one. This one is in radians rather than degrees. So, and radians tend to be a little bit harder to work with. There's nothing wrong in turning them into degrees if you absolutely have to, and then transferring things back, but we'll try to work in radian mode. So remember the angles that we want to work with are 30, which is pi over 6 in radians, 45 degrees, which is pi over 4, and 60 degrees, which is pi over 3. Now I'm going to put these all over 12 just so that we can combine them together to get 5 pi over 12 a little bit easier. This would be 2 pi over 12. This would be 3 pi over 12. I think we can see how to get 5 pi right away. And this would be 4 pi over 12. So I'm trying to get 5 pi over 12. So I notice if I add these two together, I get 5 pi over 12. So I'm going to look at the tangent of pi over 6 plus pi over 4. Notice I put those back into their simpler form. And then I'm going to expand this out, and I'm going to use these formulas down here. So I have the tangent of pi over 6 plus the tangent of pi over 4. And then in the denominator I have 1 minus, in the tangent one of them will be plus, one of them will be minus. So 1 minus tangent of pi over 6, tangent of pi over 4. Excuse me.